Here we go. All right. Hello. Welcome back. I'm Matt Russell, and we today are going to walk through the weak form, the derivation of the weak form for shear flow stabilization of a Bennett vortex. So the reason this is called the weak form, first of all, is because we're going to integrate. In general, when you're working in mathematics or hearing some mathematics and somebody says that something is a weak form, they're typically talking about an integral. And when they say strong form, they're typically talking about a derivative. This is because an integral is much weaker than a derivative. It is much more common for, let's say, for a derivative to be, and much easier to take a derivative and for a derivative to be defined than it is for an integral to be defined. So, from last time, remember that we have, in the framework of ideal MHD, the Shumlak-Hartman shear flow stabilization criterion, all right? SHC, IMHD. Recall also that we have the following axial velocity profile. With this chi-squared. This chi-squared now, because we've exchanged the Bennett profile from number density to temperature, to flow velocity, my apologies, we have a temperature dependent chi-squared, or a non-uniform chi-squared. So what we're going to do here is we're actually going to kind of diverge from where we ended up last time. And we're going to leave t in its most general form, t of r. It's just some function of r. And we're going to see what the Shumlak-Hartman criterion demands of this t in the weak case, all right, for shear flow stabilization of this profile. Now, that means we just need to take a derivative. Let's do that. So the derivative of this profile, okay, is u z naught, because that's just some constant, and it's a constant that we're going to solve for later. It is a constant, and we have on the bottom, we have, just insert chi-squared into here, cv n naught r squared over t, quantity squared, 1 on the top. And what this becomes, actually I probably need more room for this. All right. What this becomes is, first of all, oops, there go my notes. Sorry, I'm getting ahead of myself here a little bit. This becomes, first thing we're going to do is we're going to simplify this, okay? In general, when you're doing physics, you want things to be in the simplest possible form that you can. Least moving parts, the least amount of chances to make a mistake. So we're going to take this t, and we're going to get a common denominator on the bottom. And so that common denominator, we multiply this 1. And in general, when you're doing things like this, what you're really doing is you're exploiting things like t over t equals 1. Because you can multiply anything by 1 and you won't change its fundamental structure. In that case, we have t over t plus cv n naught r squared over t, right? So on the bottom, then the t on the bottom here, because it's in a parentheses squared, goes on top and becomes t squared r over t plus cv n naught r squared squared. All right? Now, we could use a quotient rule on this, but that's a bad idea. A better idea is to use the product rule, okay? So this is the derivative we're taking. That's kind of a messy -2. This derivative is what we're taking. Now remember, we have to remember that t squared, t is a function of r. So it's not 2t, that's the derivative of that. It's 2t times t prime, where t prime is the the temperature gradient in this framework. So what that leaves us with is it leaves us with 2t, t prime, minus 2 t squared, all right? We're just using the power law on this. And then we also have to take the derivative of the inside of that expression, right? It's a chain rule. When I was going through school, I did great in physics until we got to where people were using a chain rule like it was breathing. That's when I started to be like, how did that expression get to that expression? Oh, the class is gone. And then we have a t prime plus 2 cv n naught r. All right? So this is the derivative. It must be greater than 0. Let's remember that. Okay? Now, what we need to do here again is get another common denominator. We have a t plus cb n naught r squared to the negative 2 and 1 to the negative 3 over here. So we've got to multiply this guy by another factor of 1, but the factor of 1 is t plus cb n naught r squared over t plus cb n naught r squared. All right? So what that then results in is it results in 2t t prime minus minus 2t squared t prime plus 2 cb n naught r over okay? So there's going to be some significant cancellation going on here. And the first thing we can do is we can pull out, now that we have a common denominator, we can just pull it out. Pull it out front. And then what we have inside is we have just what's left in the numerator. All right, and that is, oh goodness, I'm running out of space. I also write pretty big. So the great thing here, we can see immediately, is that there's terms that cancel. This term and this term, because you see we're going to factor this 2t t prime through, and we'll get 2t squared t prime minus 2t squared t prime. And what we'll have left over is this produced with that minus that, and this is out front. And that must be greater than 0. That's the only requirement in this weak study of the Shumlak-Hartman criterion for shear-flow stabilization. So I'm going to go ahead and erase some of this. Okay? And we're going to work from here, right? So what we have then, working down here, is we have the duz dr, the shear, and I'm going to make a notice. I've gotten some comments from people that have tried to act like this is non-physical, from people that have tried to act like this is incoherent, and quite frankly, it's embarrassing to hear those things from people that think that are, you know, people with PhDs and publications in plasma science, because this is just Bennett's equilibrium. All right, it's just Bennett's equilibrium, and this is an axial flow, and that's what shows up in the Shumlak-Hartman criterion. It also makes me wonder what those people think the end game is here. So remember, we have that 2t squared t prime factor cancel. So we're left with 2t t prime cd n naught r squared minus 4t squared cd n naught r squared. Okay? And this must be greater than 0. So when you have 0 on the right-hand side of something, it's really wonderful, because anything that goes into 0 annihilates. But there's one catch. You cannot multiply, like for example, I have t plus cd and not r squared cubed on the denominator here. You might think it's just safe, we're free in the clear to multiply that by a factor of t plus c, the same factor, okay? On this side and that side, which is just another reflection of having another 1 in the problem, right? Where the 1 equals this over itself, and then 1 goes to that side, one of them goes to that side. But the problem is that, what if this is 0? And if it's 0, then we have 1 over 0. So what would make this 0? What would make this 0 is actually, remember, our boundary condition, that t of 0 equals 0. So if r equals 0, this is 0, which is a problem. But fortunately, it's not a problem, because we will simply confine our study away from the origin. And that way we avoid any singularities, and we also avoid any real problems, because our equilibrium remains well defined. This is what it is at the origin. It doesn't matter what this says at the origin, it only matters in the rest of the pinch. Okay? So with that in mind, we are looking away from 0. We are looking away from 0. We are not looking at r equals 0. At r equals 0, that's a singular point, okay, where what's going on there is simply defined by us. It's the boundary conditions that we are using. So what we do is we can just throw this guy away, because r does not equal 0. All right? I need to clean this board off. You will be patient with me, please. Thank you, dear viewers. Because we're actually almost at the end of this. We're very, very close, because even though these terms look really complicated, they're just going to, most of them are just going to be fed into that 0 on this same logic. Right, the logic that we don't care what happens at r equals 0. That's not of our interest. We are defining what's happening at r equals 0. So we can look away from it. We're free to look away from r equals 0. Okay? And so then what we have then is we have, remember, we throw that away. And you also notice there's a common factor in here of cd n naught, and I think actually, yes, this needs to be an r. Glad I caught that. Okay, what we have actually is we have a factor of cd and not r. And then what we're left inside is we are left with 2t t prime r, very important, that r, minus 4t squared, and that is greater than 0. This can also be thrown away. That's a constant that's non-zero. That's a constant that's non-zero. And this is only 0 if r equals 0, which we're looking away from. So therefore we have, and that's not good notation, but oh well. Therefore we have uz naught, 2t t prime, and this uz naught can also be thrown away, so I'll just erase it, right? And I'll move this over here, which leaves us with 2t t prime r minus 4t squared is greater than 0, right? And we have to have r does not equal 0. Okay, that's fine. This is a differential equation. It's solvable. We can integrate it. We're going to throw away a factor of 2, and what we'll be left with is we will be left with t prime r must be greater than 2t. Yeah, t prime r must be greater than 2t. Okay? So therefore we have dt dr is greater than 2t over r. We're going to do the thing that physicists do that make mathematicians angry, treat these infinitesimals as things we can multiply across. You can't really, but it still works out, right? You can, but you're doing something different. It's valid, but mathematicians don't like it. All right, so what we have then is we just have this. All right, we integrate that. Okay? And what we're left with is we're left with log of t. The natural log of t must be greater than 2 times the natural log of r. So how do we natural logs of t, so they show up, natural logs, this is actually interesting that this shows up here, because Kadamsev also ran into natural logs of thermodynamic variables for his stability condition. So what we do here is we're going to, of course, raise both of these to e, right? So we have e to the log of t must be greater than e to the 2 log of r. And when all is said and done, remember, what is e to the 2 log of r? That is e to the log r times e to the log r, right? So on the left-hand side, e to the log t is just t, right? Must be greater than r squared. And that is the weak form of the Shumlak-Hartman shear-flow stabilization criterion as applied for Bennett vortex in ideal MHD. For Bennett vortex. And again, I will remind you all that personally my favorite way to refer to these is as a Bennett-Shumlak vortex, because as you can see, it's not just Bennett, it's also the fact that we have to investigate the structure of the Shumlak-Hartman criterion. Anyways, thank you all for watching. I think this video was a lot shorter, and that's good. And anyways, make sure to like and subscribe. I really need your support. And I will see you next time. We will be working in the strong form next time. The strong form is when we do not try to integrate, as we've done here, but rather we take a power law form and then we study the consequences. Anyways, thank you all for watching, and we'll see you next time.